So today I want to start wrapping up the course in terms of its final objective. I don't know how much proofs I will do in this course, but I'll try to give you an idea of the fundamentals of subject. So far, we've been trying to do the following. So we've been studying probability. So probability. So the way we've introduced it to ourselves is kind of the study of models. Study of models for presumably random experiments. When the model is not known, when the model is known. So we have done this in many ways. We've set up various schemes. One is we had sample spaces. We defined it as the space of all outcomes, events, and probabilities. From that, we defined for convenience sake, we defined random variables. And from this, we branched off into two parts: discrete and continuous. And we studied how to understand each of these setups as we went along. So now, on the other hand, for applications, it's okay. For the lack of a better word, I'll just call it statistics. So in statistics, what happens is that the model is not fully known. So when the model is not fully known, so in probability the model is known. You try to understand what the model is. So when the model is not fully known, in statistics, what one tries to infer about the model the unknown aspects. Okay, so one tries to infer about the model so let me call it about the unknown. So about the unknown aspects, because everything, what unknown aspects you will understand in a second. What you do is you based on the outcomes of the experiment. Okay, based on the, so I'll write it in green, the observed outcomes of the experiment. So all you have is the experiment. You don't know what the model is. You just see some observed values, and then you want to infer something about the model in statistics. And that's where the connection comes in, and how we build the probability model and why it's relevant to the statistics application. Something we will discuss in the next video. So that's the two broad philosophical ideas. So now what I'd like to do now is from given these two sort of ideas or notions of the two fields, let's try and develop notations to sort of see how the connection develops. So let's say we perform an experiment n times. So this could be in many ways. So let me write it in blue. So suppose we perform an experiment n times. So this could be like the Bernoulli trials that we did. We toss a coin n times. We have independent trials. So let's just do independent. So this we have already seen before. This is like example is the Bernoulli trials, right? The Bernoulli trials. We did a long time back. We said that we toss a coin n times, and then each time we note down the outcome. It's head or tail. So now, so what you do is once you have this, let's say you let x1, x2 up to xn denote the outcomes. Okay? Of the experiment. Now, two things we observe. One is that since it's the same experiment, we're performing again and again. Each xi has the same distribution. Because it's doing the same experiment, and then it's also independent. All other xj, j not equal to 1. So now such a sequence we would refer to as an Iid sequence. So xi, I bigger than equal to 1, you call it an Iid sequence. So Iid sequence I is for identical, so independent. Sorry, first I is for independent, and the ID is for identically distributed. And so that's the setup we have. So we perform experiment times, and this is all we know about the experiment. Right? So we don't know. So here in the Bernoulli trials, we discussed it in terms of how the model was. Here the model is not known. All we see is x1 through xi. But we know several facts. We know xi is same distribution, and they're independent of each other. So what can we do with this? Okay. So how can we infer something about the model? So the first thing we could do is we could do some simple summary, right? So what all can we do? Let me write the questions down. What all can we do to understand all these experiments? So first question is what can we understand about the model? Can we understand about the unknown model? So unknown model, I'll use a different word now. I will use the unknown distribution, because that's, we know the same distribution to try to understand the x's. So if you're in a statistics class, the first thing you would do is, okay, you say you have xi's, you'd first calculate x bar. X bar is the sample mean. Let's say sample mean. You do x1 plus x2 plus x3 up to xn, divide by n. Then perhaps you would find the maximum, right, of the x1 through xi, largest guy. You would prime the minimum of x1 through x1, the smallest guy, right? So let's call this as x max and x min. Okay. You do this. Then maybe if you're a little bit more adventurous, you would go and do, let's say, find the median. You find the median and the quantiles of this data set, and so on and so forth. So these are all immediate, what I would call as the summary facts that you find about it. That can be computed. Now the key thing is that what do they tell you about the distribution? So where do they? So let's come back. Let's come back to this idea that we had before. So what are we assuming while doing these calculations? So here, let me just briefly digress a little bit. So when you do sample mean, what are the assumptions you're making? to infer. From some. Yeah. Okay. So that I'd like to understand. So let me just quickly just recap the broad question again. So the broad question was in probability, it's a study of the model. The model is known. In statistics, when the model is not fully known, one tries to infer about the unknown aspects of it based on the observed outcome. So I started this idea that I perform the experiment n times, and I have n1 through x1 through xn, and from this I know that sample mean is x1 plus x2 plus xn by n. The maximum is something, the minimum is something. I can find the median of the data set and the quantiles. And this gives me some understanding of how data distribution is. But to do this, I'm making some assumptions. So let me try and understand what the assumptions are. And from the assumptions, how do I get to the real model? So we go back. So now, let's try. So now, here are some keys. Okay, so here are some keys. So what are some? So I want, like I finished off the last part by saying I want to know what are the key assumptions. So here, let me start here. So here are some keys. To the question or understanding from summary. So one assumption, if you want to understand the sample mean as saying something about the random variable, so one assumption we make is that there's equal probability of every outcome. So equal probability at each observed outcome. So that's how we compute the sample mean. I give 1 over n value to every problem, every point. So then there's something called what we are working with is typically called, if you have a data set, you're working with what's called the empirical distribution. So that's the feature. So we say S, the distribution is on the set, S, the sample space outcome so far, we only know x1 through xn. This is all we have. So that's a set S. Right? So note I've written like a set. So this could involve repeat observations. Okay? So may include repeat. So you could observe the same outcomes in every experiment, but in different trials. But as a set, it's a sum set. You don't have endpoints. So the empirical distribution is based on the discrete distributions of S. On S, so what is the discrete distribution? Its probability mass function is given by So I'll call the mass function as f of t as just the sum over all possible t in S. I'll do 1 over n, the number of I, such that xi is equal to t. So look at all the t's, and I look at how many points of xi are at t. I compare them, I count them, I divide by n, and that's the empirical distribution of the point. So there's some subtleties to note. Just this if you're a probabilist, you're a little bit careful. That one is that this depends on the sample. So this depends on the sample. So if I go and do the experiment again, in trials of it, I might get different exponent extent, and then the sample space S will change, and then my empirical distribution also will change. So in that sense, this is kind of random. It's not deterministic. It's determined by the sample. And one other interesting aspect is that we don't make any assumptions about the model. Okay? We don't make any assumption about the underlying distribution. Any assumption about the underlying distribution at this point in time. Okay? Because my only information we have about the random variables, about the experiment and the model are x1 through xn. Nothing else we know. So this whole feature of inferring from this empirical distribution is called descriptive statistics. That's what everybody does. So inferences based on empirical distribution is called descriptive statistics. Called descriptive statistics. So then the philosophy is the following. So you think that, okay, intuitively, what do you know? What do you understand? So intuitively, once you understand this idea that the empirical distribution gives you what's happening till now. So intuitively, one can understand the following idea. Suppose as n gets larger and larger, that is, as n goes to infinity, that n gets larger and larger, that is, n gets larger and larger. That is, I get more and more samples from the experiment. Then we will get closer to understanding the true distribution. We will get closer to understanding the true distribution. The true distribution. So this is the fundamental idea. I'd like to sort of the last green part is what I'd like to justify. That as n gets larger and larger, your empirical guy is getting close to your true guy. In what sense we will try and justify this in the next video. Okay. So now let me make one let me try and get to the probability. So now this f is clearly a PMF, right? Because it's non-negative, it sums up to 1, and it's 0 below the minimum of points in S, it's 1 after the point, it's outside the maximum of S, it's only supported on the points of S, and so on. Right? So maybe here I made a small error, let me just correct it. So f of, so I should say, here I would just to be a little bit careful, I think I made a small error. So I would say, right, so here I should say, so the empirical distribution is count the number of points in T. So I would just not have this sum here. I'm sorry about that. This is not the sum. So I would just do f of T is just the number of points at here is this mistake here. So I go to f of T, I just compute the number of points. Yeah, it's just this, and this is for all T, yes. That's what they have taken. PMF. So now, suppose I have a random variable y. So let's go back to the model. Let y be a random variable. with probability mass function f. Okay. So now, if y means y is random variable, it means probability of y, it is probability of y equal to t is equal to f of t. And in some sense, I could just go back here and just say for any t in the real line. Of course, xi is only in S, so I could just write like this, and then f of t is this, and then and 0 other ones. Probability y equal to f of t, and then we know that the range of y is S. Suppose I take random variable like this probability mass function. Now, if I do the random variable, what's the mean of the random variable? So the mean of the random variable y is going to be E of y, that's value, is just sum over t in S, t times the probability of y equal to t. But that's the same as t in S times t times the number of points in I such that xi is equal to t divided by I. That's what f of t is. Now this is going to be equal to what now? This is going to be equal to, if you just stare a little bit, all I'm doing is I'm running through everybody in S, I'm multiplying by the number of points I, so xi is equal to t. So this you can sort of rejuggle if I remove the sum. So let me write this way. So I think of it as sum over t in S. I look at this inside part. We call this in blue. So I look at the inside part as the sum over I equal to 1 to n indicator of xi equal to t. That's just the number of points here, divided by n. And now if I integrate in the sum, I will just get the sum from I equal to 1 to n. T times indicator xi equal to t, I can just replace it by xi and divide by n. Well, that's all right. Maybe I can do it in 2 steps. So I'll have indicator, so I'll have this as the sum. So 1 over n comes out. I'll leave the 1 over n outside. For the black, the sum over t in S, t times indicator of xi equal to t. This is going to be equal to the sum from I equal to 1 to n xi divided by n. Because t times indicator xi equal to t is just xi. So this we know is just x bar. So it means the mean of the random variable y with PMF f is x bar. So something. So the underlying empirical distribution has mean given by x bar. So for the as far as the underlying distribution is concerned, the empirical distribution is concerned, the true mean for it is x bar. That's what I'm trying to understand. So let me just quickly recap what we did. Let me just sort of get back to the top. Show you 2 things. So this is the idea we're trying to understand. So now I have an empirical data set, and I know its sample mean is this, is x bar. But what happens is that if I assume that the entire distribution is contained in x1 through xn, so then I can say my S is x1 through xn. And once I do that, then I know immediately that that the PMF, if I define an empirical distribution with the PMF f given by just counting the number of points at each point t, then I call that capital F. Then I have a random variable y that whose PMF is given by f. So if I take a random variable y PMF f, it turns out the mean of y is just x bar by itself. So that's one observation we have. kind of a nice observation. That is, if you have a data set x1 through xn, the understanding is that as n gets larger and larger, you are going to converge to a true distribution, and the true distribution, in some sense, is captured by the empirical distribution in the following way so far. That's where we are. Very nice. Very good. Okay, very nice. So now let me do one fact about x bar. Let me come back to x bar. So now let me just discuss a couple of things about x bar. So here's an interesting theorem. Let's just try this to solve an obvious theorem. Suppose now let's so I should just I would just call it sample mean. I won't call it variance. So now you let x1 through xn, x2. Now let's assume something about the model. Let's say x1 and xn be an IID sample. IID, random variables, let's say. That is, they all the same distribution. Now let's assume something. Let's assume that the mean is finite. That is, E of x1 is equal to mu is finite. And let's assume the variance of x1 is also finite. It means each of them has finite variance as well. Now let's consider x bar. What's x bar? X bar is x1 plus x2 plus xn by n. That's what I did, right? That's the sample mean that I did. Now, what is E of x bar? Let me see what's E of x bar. What is E of x bar? And what is variance of x bar? So let's try and do the proof and see the result. So here's the proof. So here, E of x bar means what? E of x bar is just E of x1 plus x2 plus xn by n, and that's just the linearity of expectations, E of x1 plus E of xn by n. But they're all IID, so they're all equal to mu. So it's just mu plus mu n times divided by n. And that's just going to be n mu by n, and that's going to be mu. So E of x bar is just the same as the true mean. So on average, x bar represents the true mean. So if you sample many times, you should get x bar should be mu. The next one is the following. What's the variance of x bar? So what's the variance of x bar? Variance of x bar is variance of x1 plus x2 plus xn by n. This 1 over n is a constant. So we know from the facts about variance, right, these facts about variance, this is like 1 over n squared times the variance of x1 plus x2 plus xn. The n squared, n comes out of n squared. Now again, another fact about variance, you know that since they are independent, since xi's are independent, and we know that the variance of x plus x1 plus x2 plus x1 plus x2, let's say, is going to be just the sum of the variances if they're independent. So what we'll get is in this case, the variance will just add up. So it will be 1 over n squared, that's outside. So 1 over n squared. And then all I'll get is sum over I equal to 1 to n, variance of xi. But you go back to the problem, each one was assumed to be a sigma square. So therefore, you come down and then you show that this guy is going to be equal to 1 over n squared into n times sigma squared. So that's going to be sigma squared by n. So the variance of x bar is sigma squared. So the first thing we observe, that is the sample mean on average will be the true mean. So let me erase this, true mean. And its variance is sigma squared by n. Variance. So let me just recap this observation. So what was the remark? The remark is the following. So how do you interpret E of x bar equal to mu? E of x bar equal to mu, the interpretation is, on an average, the quantity x bar is accurately describing the unknown mu. That's one interpretation of the x bar. So in statistics, this is called, one says that x bar is an unbiased estimator of mu. This is what one would say in statistics. So this is the statistics terminology when this happens. You're trying to estimate a parameter in the model, and you have a statistic from the data set that estimates it. On a true, its average is going to be equal to the true parameter. You say that it's an unbiased estimate. That's just a remark in statistics. And we also know one thing. We also know variance of x bar. So let me write down this in black. Okay. We also know variance of x bar is sigma squared by n. So what does that mean? That means the statistic, the sort of understanding is that as n goes to infinity, the variance of x bar is converging to 0. Right? That's what this means. That means the spread of x bar is getting smaller and smaller as n goes to infinity. That is, first we write SD of x bar goes to 0 as n goes to infinity, which implies the spread or the range of x bar, that's what we called before, right? The range, the standard deviation represents the range, right? The range of x bar gets smaller and smaller, as n gets to infinity. Thus, with large n, x bar reflects the true value more accurately. Thus, x bar reflects the true value more accurately. The true value mu more accurately. So let me write it down. Let me erase this. Sorry. More accurate. So this in statistics, they say it differently. The way I say it is, they say that in statistics they will say x bar is a consistent estimator of mu. So let me just quickly recap again. So now, so what did we do here? We let me go and do a split view. Let me start again. So, like we start off with the beginning, in probability the model is known. In statistics the model is not known. Then we said that, okay, we perform an experiment. We have x1 through xn observations on the left hand side, and then that's all we know. Nothing else we know. This is like in the olden days we did this Bernoulli trials, but now we just have x1 through xn. From this, what we know? We know sample mean, we know minimum, maximum, we know median, quantiles, and so on and so forth. That gives you some idea of where the distribution is centered in and how the distribution is behaving. But what's the assumptions we are making for this? We are assuming that by doing this, inferences from the sample, we are assuming that every point has the same value, probability of the weight, which is 1 over n. That's what we do, assumption, equal probability each outcome. From this, what we would get is the empirical distribution, which is what we are working with. That is the probability mass function given by f of t, which is 1 over n times the number of people at t in s and 0 otherwise. This depends on the sample. Every sample will give you a different empirical distribution. But the interesting idea is that we make no assumptions in the model. Now, how do we go from here to the true model? So what I said was that the empirical distribution has this following property, that if y is a random variable with PMFF, then it turns out that the mean of y, if you do a simple computation, becomes x bar. So in some sense, by just the fact that we make no assumptions in the model and put 1 over n each weight, this ensures that your artificial empirical distribution is going to be equal to x bar. So what properties of an x bar can we identify if we knew something about the model? Suppose the model had true mean mu, like we had here, then we found out that the mean of x bar was going to be equal to the true mean, and the variance of x bar was going to be sigma squared by it. And the way we did this was a simple computation. We used the properties of expectation, linearity, and in variance, we have two facts about variance. One is that if it's independent, then the variance sums up, and a constant gets out by a square. So what are the two crucial facts about this? Once you have this idea, is that once you know these two things, the idea is that E of x bar is on an average the quantity mu, and since its variance is going to go to 0, the range of x bar is getting smaller and smaller. So that's with a large n, x bar reflects the true value. So these two things we have sort of understood in this from this empirical statistics. Okay, very good. Now let me try and see how to sort of make these ideas rigorous in probability. Let's try and make the last two lines rigorous. Let's say these are not rigorous. So let me just go back and recall a couple of things. Let me recall what we were doing last class. In fact, so let's recall. So we know this following fact, right? Let's say if z is a random, let's say so z, let me use the word w. W is a random variable, and let's say E of W is mu, and variance of W is this is sigma squared. They're both finite. Then we saw this Chebyshev inequality, right? Chebyshev. I forget the spelling of Chebyshev. Let's see. I'm going to go back to the spelling may be wrong. I'll just leave it as the spelling is wrong. Sorry about that. So inequality, we know that the chance that x minus w minus mu bigger than k times sigma is less than equal to 1 over k squared. This is true for all k. This is what we discovered last time. So in the above, let's try and see what we can say about the above. So now I'll do the following fact. So I'll say I want to understand this remark. Right? There is a more precisely. As E of x bar is mu, variance x bar sigma squared by n. What can I do? What can I understand by this statement? So now the first thing is, let me do the following. So let me take a small epsilon. Okay, epsilon bigger than p given. I want to understand how far is x bar from mu. So let's consider x bar minus mu is bigger than epsilon. Okay, so I want to consider the event. Okay, let's consider the event. Let's consider the event that x bar minus mu is bigger than epsilon. Now, if I want to do, now we know from the previous facts, what all we know? We know two things. We know mean of x bar. Sorry, we know mean of x bar. We know mean of x bar is equal to mu. We know the variance of x bar is equal to sigma squared by n. And we also have the Chebyshev inequality. The one that we discussed just now, right? We have these three things. So from this, can we identify the probability of it? Let's say the probability of the event x bar minus mu is bigger than epsilon. Suppose I want to understand that. So if I want to emulate the Chebyshev inequality, in Chebyshev I have w minus mu is bigger than k times sigma. So what I could do is I could think of this as, let me go a little bit, is equal to, rather than black now, probability that x bar minus its true mean, right? Now in Chebyshev's, I need a k, right? So I put a k is that I would just say I had epsilon here. So the epsilon I need a sigma here, because in Chebyshev's I need a sigma, right? So what I would do is I would just say I would have a sigma, but here I have epsilon. So I have to multiply and divide by sigma. So I'll just do epsilon by sigma. Right? That's all I do. And this I would think of as my key. Okay? I would think of as my key. So let's say let k equal to epsilon by sigma. You apply Chebyshev. Let me write this in black or green. Let's say. So let's say k equal to epsilon by sigma and apply Chebyshev. What to get the above is less than equal to, so the above less than equal to 1 over k squared, right? So it's 1 over k squared. So it's 1 over k squared. But what is k? Epsilon by sigma. So I think I made one more error. The variance was sigma squared by n, right? So I should do sigma by n. So I should do this sigma by n here, and here also I would have in the black also I would have sigma by n. So that's the variance of x bar. Sigma squared. I should do root n. Sorry. Let me just I'm making a mess of this. Let me go back. So this is going to be equal to. So I let k be equal to. Let me come back and erase this also. So I want to write it as k times the standard deviation, variance sigma squared by n. So I want to write sigma by root n. That's what I want to write as. So k would be in terms of epsilon. Epsilon was here, so I have to multiply and divide by add epsilon. So I have to multiply and divide by root n by sigma. That's what my k is. That's what. So 1 over k squared Chebyshev's. K squared 1 over k squared means I get sigma squared by epsilon times n. So this let me write it in blue so that I have the whole thing clear. So this x bar is sigma squared by epsilon squared times, that's what I get. So what have I got? So this would imply probability of the event x bar minus mu is at least epsilon is less than equal to sigma squared by epsilon. So now we also know a priori that the probability is always non-negative. So I have 0 less than or equal to this is less than or equal to that. So it's an interesting fact immediately that this would imply that the limit as n tends to infinity of the event x bar minus mu bigger than epsilon is going to be equal to 0. And this is true for any epsilon. So it implies for any epsilon positive. So this is one way of understanding precisely what we mean by saying x bar gets to mu as n gets larger and larger. There is a chance that x bar is away from mu by epsilon is going to go to 0 as n goes to 0. Maybe I'll take a short break. I'll come back and sort of make the statement more rigorous.